Swayam Prabha. Digital India. Educated India.
So, we will talk about cryptanalysis on substitution cipher. We have seen the substitution cipher. It is basically the plain text is plain text hypertext and plain text hypertext or a set of alphabets. And the key is basically key space is basically the set of all alphabet. We denote this by A. So, this is basically set of all permutation, where phi is a permutation, on A. So, it is basically a bijective mapping from A to A. So, then we have seen if we take a permutation and then the encryption is basically this is the key k. So, encryption E of k on x is an alphabet is basically phi of x, and this is the encryption, and decryption is d of. So, if this is y, then y is basically phi inverse of y. So, which is basically phi inverse of phi of x, which will give us x. Okay. So, this is the substitution cipher, and we have seen some example on one example on substitution cipher in the earlier class. So, now the question is how secure is this cipher is. Now, this is the key space is the set of all permutation from set of all permutation on this set of alphabets. Now, the question is how secure this cipher is. So, we want to do the cryptanalysis, especially we want to do the frequency analysis on this cipher. So, let us talk about whether we can have a brute force attack or exhaustive search attack on this. So, let us talk about the key space. So, what is the key space of this cipher? Key is the set of all permutation. So, there are factorial 26 permutation. So, this number is basically 4 into 10 to the power 26, which is approximately 2 to the power 88, which is huge, very large number. So, this many permutation are possible. So, if one has to go for the brute force method or searching in a key space, the Oscar, then Oscar has to try for all possible permutation, and there are this many permutation. So, Oscar will choose one permutation and check whether getting a meaningful text or not, then choose another permutation and check whether getting a meaningful text or not. So, this way Oscar has to talk about try for all possible permutation, and which is very expensive in the sense that computationally it is very hard, because 2 to the power 88 is a large number. Okay. So, but this way brute force method is not possible to attack this now, but there is a attack model which is called frequency analysis. This can be mount for this attack, because our text is the English text. We know the plain text and ciphertext are basically English. So, in the English text there is a pattern of the frequency of the alphabets. So, if we analyze the English big text, then we can see this phenomena is the E is the most frequent letter occurring in English text. So, and this way, so if we know this pattern that E is the most frequent letter, so this is called frequency analysis, then we can have a cryptanalysis on this substitution cipher. So, this is suppose we have a long ciphertext which is a which is outcome of a long English text, and the challenge is to decipher it, and it is encrypted using monoalphabetic substitution cipher. Monoalphabetic, I will come to that, what is the monoalphabetic. In monoalphabetic, alphabet is mapping to a fixed alphabet. So, if T is mapping to E, then T cannot be mapping to D, this is not possible. So, this is called monoalphabetic. Every alphabet is mapping to a fixed alphabet, it is not mapping to different alphabet. Okay. So, we have this phenomena, this for English text, people have observed that E is the most common letter. So, if you take any English big text and if we just do the frequency count on this of the letter, then we can see this picture that we just do the frequency count, and if the letter coming we just put like this, this way we do the frequency count. No? How many times A is coming, how many times B is coming, how many times E is coming, like this. So, it has observed if you take a big text, then E is having high frequency than T, than A. So, E is having high frequency than T, than A, like this. So, this is a observation on the English text. So, we want to apply this on our cryptanalysis of substitution cipher. So, this how we can apply this. So, we have a long ciphertext which is basically we know it is coming from a English. Now, if we see, now we count the frequency of that ciphertext and we count the letter of in that ciphertext the letter. If you observe, J is coming more frequent, J is having more frequency in that ciphertext, then we have to see, we have to guess that J is basically E was encrypted to J, like this, and then J is likely to the substitution for E, and then P, if we see P is the most frequent, next most frequent word, then we can see that T is the next high frequency letter in the English text, then we can say that T is substitute to P. So, like this we will do this frequency analysis, and we will just, there will be some gap, and those gap we need to fill up by our intuition or by some trial and error method. So, we will take an English text. So, let us take this ciphertext. This is a ciphertext Alice is sending to Bob. Now, what we will do? So, on this ciphertext we will just do the frequency count, so of the letter. So, if you do the frequency count of the letter, just A is coming how many times? No, A is not coming, B is coming one time, like this, C is coming this, like this. So, we observe that Z is coming 20 times. So, that means wherever Z is, it is intuition that Z is basically E was substitute to Z, because E is the most frequent letter in the English alphabet. So, wherever Z is coming, we will replace by E. So, that was in the original plain text, because E. So, if we convert the corresponding plain text, if we see, that is a English text. So, in the English text, E is the most frequent letter. Now, here Z is we are encountering as most frequent alphabet. So, that means it is quite clear that the E was mapped to Z, and then who is the most frequent? Then this is 16, then M. So, that means T was mapped to M, like this. So, if you do that, so this will be, so E, so this will be the corresponding letter we place, E, D, N, like this. Okay. So, this is the first part of this first sentence of the ciphertext, this is the second, third, fourth. So, this we just got some of the letters of the plain text, and then we will try for together, I mean by letters. If we try that also, then we can fill up something more, and then this way if we continue, we can fill up and we will use our intuition to fill up the remaining thing. So, if we got some blank, now it is the question of filling the blanks. We know this is the English text, so it should have a meaningful thing. So, that means finally, once we got this from this frequency analysis, then now we can guess, because this should be a meaningful English text. So, this should be our. So, our, this should be F is missing, friend, this should be from Paris. So, this way one can get the plain text. So, this is the frequency attack on frequency analysis on substitution cipher, and this is possible because substitution cipher is a monoalphabetic cipher. Monoalphabetic means each letter is mapping to a unique alphabet, each alphabet is mapping to a unique alphabet. So, yeah, each alphabetic character is mapped to a unique alphabetic character. So, that is why it is possible to do the frequency analysis on this. On the other hand, to prevent this, what we will do, we will talk about what is called polyalphabetic cipher. So, in polyalphabetic cipher, it is basically we use, the idea is to use the different monoalphabetic substitution while moving through the plain text. So, we just use different monoalphabetic cipher while we move to the plain text for the encryption purpose, and then it will give us a polyalphabetic, in a sense that we will see in a plain text. So, E is not mapping to a fixed alphabet. In the different position, E sometimes E is mapping to M, E is mapping to N, something like that. So, we will come to an example. So, this is called visionary cipher. First example of polyalphabetic cipher we will talk about. This is visionary cipher. Okay, so this is the idea is to use the substitution cipher, basically SIP cipher, while we are moving through the plain text. So, here let M be a, this is the size of the window. So, we are blocking the plain, we are breaking the plain text into blocks. So, each block size is just M bit, M is a M be a integer, positive integer. Okay. And then we block the plain text into m bits, say. So, our plain text is basically Z26 to the power m, which is same as the ciphertext space, which is same as the key space. So, each key is a this many bits. So, a key is basically K1, K2, Kn. So, this is basically coming from Z26 to the power m. To the power m means it is a Cartesian product, Z26. Okay. So, we will use the substitution cipher while moving through the plain text m bit blocks wise. Okay. So, this is the key. Now, we take a plain texts are also m bit. So, we take a plain text say k or x, x1, x2, xm, this is the plain text, it is also m bit vector. Now, the encryption use on this basically. So, it will also be a m bit, because ciphertext space is also m bit. So, it is basically bitwise. So, x1 plus k1 comma x2 plus k2 comma xn xm plus km. Okay. And decryption is basically, so this is say y, this is say y1, y2, ym. So, this is y vector. Now, decryption on y vector is basically y1 minus k1 comma y2 minus k2 comma dot 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 ym minus km. Okay. So, this is the decryption, and each of this plus and this subtraction are under mod 26, because we want this guy should be Z 26. So, each operation here, whether addition or subtraction, each operation is under mod 26. Okay. So, this is the visionary cipher. Now, we want to apply on some plain text. So, let us take an example of a plain text. So, yeah, so suppose the plain text is the English text. So, plain text is the English text, and so we have the correspondence between English text and Z2. So, that is basically this is Z2 Z26 0 1 2 up to 25 and English alphabet. So, this is basically A, this is B. So, this is the correspondence we have used between Z26 and the set of all alphabets. So, this is the one-to-one correspondence between English alphabet set with the set Z26. Okay, now we have to choose a m. Suppose m is 6, and suppose our key is say Cipher. Cipher means 6 letter. Now, we can replace this by this one-to-one correspondence. So, it will be 2, 8, 15, 7, 4, 17. So, this is our key K, 2, 8, 15, 7, 4, 17. 17 is the basically the this under this correspondence, it is basically R. Okay. So, now suppose we want to encrypt a plain text, this is our plain text, say this crypto system is not secure. Suppose this is the plain text. So, what we do? We just convert this English alphabet to digit, I mean the integer. We know the correspondence, A is going to 0, B is 1, C is 2, like this. We know this one-to-one correspondence here. So, this correspondence we will apply and we will get the corresponding digit integer bits. So, these are the integer bits we are having. Now, this we have to break it into 6 bits block. Bits means each bits is a integer, because we are moving through the plain text and we are applying a mono alphabetic cipher, that is the SIP cipher we are using. So, this is the first block, this is the second block, like this. Last block we have only three numbers, 3 digit, 3 integers, so that is fine. So, now we know the key is basically Cipher. Cipher is basically our key, and key is 2, 8, 15 this. So, this we are going to add with these blocks. So, if you do that, so here 2, 8, 15, 7, 4, 17, 2, 8, this is the key. So, on each block we apply this and we get the corresponding ciphertext block. So, this is basically we are adding mod 26. So, this is 17 plus 17, 34, 34 mod 26 is basically 8. So, this is the ciphertext. So, this is first block of the ciphertext, second block of the ciphertext. So, finally, we convert this integer again into the alphabet by that one-to-one correspondence, and so 21 is basically V, 15 is P, 23 is X, 25 is Z, like this. Okay. So, this is the ciphertext corresponding to this plain text. And why this is polyalphabetic? In the polyalphabetic, we know that one alphabet can map to the different alphabet. So, if you come here, if we observe this S is mapping to Z, this S is mapping to W, this S is mapping to U, this S is mapping to Z, this S is mapping to again Z. So, J and this is Z. So, that means it is not a fixed number. So, S is not mapping to a fixed alphabet, S is mapping to different alphabet over here. So, frequency analysis could be difficult in this case, and this way it is called polyalphabetic cipher, because it is not giving us a unique correspondence. So, a letter is not going to a fixed letter, it may going to a different alphabet. Okay. So, now we will take another example of polyalphabetic cipher. So, polyalphabetic cipher is difficult to break by the frequency analysis, because we know this E we know the most frequency letter, but if E is going to some different alphabet. So, then in the ciphertext frequency analysis will not give us the proper result, like proper frequency that E this letter should come from E, like this. Okay. Okay. So, next one is what is called transportation cipher. This is basically also called the permutation cipher, also transportation cipher. Okay. So, this is also called I think this is called permutation cipher also. Okay. So, transportation or permutation cipher. So far we have seen the substitution method. Now, this is coming from the transportation technique, which is basically the rail French technique. So, what is rail French technique? Suppose we have a plain text like this: meet me after the party. After the party is over. Okay. So, what we do? We suppose we have a 2 by 2 matrix. This is rail French. This is called rail French. This could be 3 by 3, 4 by 4, like this. So, we will put this in this way, like this rail track. So, M E E T M E A F T E R T H E P A P A R T Y I S O V E R. Okay. So, we have this plain text, this is the plain text. So, this is rail French technique basically. So, what we are doing? We are just reading this in a column wise. So, this is the M meet, like this way we are reading, and then this way we are placing in a matrix, 2 by 2 matrix. And then to get the ciphertext, what we will do? We will read it by row wise. So, the ciphertext will be coming from read it by row wise. So, if we read it row wise, this is M E M A T R H P R Y S V R E T E F E T E A T I O E. So, this is the ciphertext, and from here it is quite, I mean, it is not so obvious to guess what was the plain text. So, this technique is called rail French technique. This transportation cipher is coming from this idea. So, this could be instead of 2 by 2 mat 2 by 2 order, we can have 3 by 3 also, like this could be 3 by 3 or 4 by 4 like this. So, if it is 3 by 3, then we have we will put it like this, M E E T M E A F T like this, and we will read row wise. So, that technique is called transportation rail French technique, and this technique idea we will use for this what is called transportation cipher or the permutation cipher. So, let us formally define this cipher. Okay, so, this is basically we also have a m we choose. So, this is step 1, m is a positive number, positive integer. So, our window size is m, and here also similar to visionary cipher, here also our p ciphertext space is basically Z26 to the power m. Okay. And here our key space is basically set of all permutation from 1 to m to on this set. So, it is basically set of all bijective mapping from 1 to m to itself. So, this is a bijective mapping. So, this is basically set of all permutation. So, how many permutations are there? So, there are m numbers. So, there are basically factorial m permutation. Okay. Now, what is now the encryption? Encryption, for encryption we need to choose a key. So, we take a permutation which is say phi from this key space. This is our key. Now, we define this encryption by this E of. So, we need to take a x is a plain text, x is coming from x1 x2 xm. So, each plain text is a m bit number. So, this is basically we are randomly not random words, I should not use, it is basically a shuffling of the positions. So, E of x is basically x phi of 1 comma x phi of 2 comma x phi of m. So, basically we are this numbers we are just linearly permuting. So, maybe phi of 1 is 3, phi of 2 maybe depending on the phi permutation, it could be that way. So, this is the encryption, and the decryption is, so dk of d of phi y. Now, say this is y. So, this is say y1, this is the ciphertext y1, y2, ym, and say this is the ciphertext. So, the decryption will be on this is a y vector ciphertext. So, dk of y is basically y phi 1 inverse 1 and y phi 1 inverse of 2 like this, y phi 1 in phi inverse of m. Okay. So, basically we are suppling these numbers, and then we are applying the we are resuppling it to make it original one, I mean the original position we are making back, where phi inverse is the inverse of this phi, inverse permutation is the inverse permutation of phi. Okay. So, this is the way. So, here we are just taking a m bit m blocks like this. So, this is our plain text space and this is our set of keys. set of all permutation basically. So, we choose a particular key, we choose a key k, and this ek of this is basically the permutation this, and dk of this is this, and phi inverse is this. Now, let us take an example. So, suppose m is 6 and we choose a permutation which is basically 1 to m, it is permutation 1 is going to here, 3 is coming here, 5 is coming here. So, whatever x 5 it will come here, whatever is x 1 it will come here. So, basically it is a shuffling, I mean this linear permutation on the x 1 x 2 x m. So, this is one permutation we are choosing, and then the corresponding inverse permutation is this. Now, suppose this is our plain text, defend the hill top at sunset. So, this is our plain text. So, if we have to apply this permutation cipher, we have to break it into 6 blocks, I mean the blocks of each 6 digits. So, D, E, F, E, and D. So, this way we just break it into 6 bits. So, last one if it is 6 it is okay, otherwise. So, now we have to apply this on this each of this block, we have to apply this permutation. So, this permutation is basically, so let us take this an example. So, if you just come back to our permutation is so 1, 2, 3, 4, 5, 6, and this is basically 3, 5, 1, 6, 4, 2. Okay. So, now this is our permutation. Now, if we take this defend D, E, F, E, N, D. Okay. This is one block. So, now this is x 1, x 2, x 3, x 4, x 5, x 6. Now, this will go to the, this is the plain text block, first plain text block. So, this will go to the x phi 1, x phi 2, x pi 3, x pi 4, x pi 5, x pi 6. Now, x pi 1 is basically x 3, this is x pi 2, x pi 2 is basically x 5, and x pi 3 is basically x 1, x pi 4 is basically x 6, this is x 4, this is x 2. So, that means x 3 will come here, x 5 will come here, x 1 will go there, here, and x 6 will come here, x 4 will go here, and x 2 will go there. So, we can just write. So, this is basically F, this is N, this is F N D, this is also D, and this is E E. So, this is just a linear shuffling on this digit. Okay. So, if we just apply that, we are getting this is the first block. Similarly, we apply pi on this, we get this. Similarly, this like this. So, finally, this is our cipher text corresponding to that plain text. And for decryption, we have to use the inverse permutation. So, we take this block and we apply phi inverse. So, we will get different. Similarly, we have to apply from this block, we apply phi inverse on each this. So, we get this. Okay. So, this is the this is called permutation cipher or transportation cipher. Thank you.